This is now lecture number 19 in our course on transport processes. We had in the last two lectures looked at diffusion coefficients and constitutive relations. Okay. Firstly, the two mechanisms of transport, convection and diffusion. Convection due to the mean velocity of the molecules, and the flux is equal to the component of the velocity perpendicular to the surface times the density of whatever is being transported, whether it is mass, momentum or energy. Diffusion flux due to the fluctuating molecular velocities, not the fluid mean velocity, okay, the fluid velocity. As I had explained to you in a previous lecture, the fluid velocity is the vector sum of the velocities of all of the molecules, whereas the fluid fluctuating velocity is the molecular velocity minus the mean velocity. The convection flux is quite easy. It is equal to the velocity perpendicular to the surface times the density of whatever is being transported. Diffusion flux due to molecular velocity fluctuations only when there is a variation in the density of whatever is being transported, mass, momentum or energy. If there is no variation, the transport in one direction will be equal to the transport in the other direction, and there is no net flux. The variation comes about because the molecules, in the case of gases that are going across the surface, the molecules going upwards are coming from a location a little bit below the surface, whereas the molecules that are going downwards are coming from a location that is slightly above the surface. The concentration of the molecules at these two locations is different. Okay. You have different concentration of molecules at these two locations when there is a concentration variation across the surface, and this results in a flux. That flux is approximately equal to the difference in concentration between these two locations times the root mean square of the fluctuating velocity. The root mean square of the fluctuating velocity in gases we know is equal to square root of 3 kT by m, where T is the temperature. That is how the temperature is defined in gases. Therefore, from this the flux is equal to the root mean square fluctuating velocity times the concentration difference between these two locations. That concentration difference is the mean free path times the gradient of the concentration, the mean free path times the variation across the surface. So, therefore, we get expressions that end up being of the form of Fick's law. Okay. That is that the flux is equal to something times the gradient in concentration. That thing in front is the diffusion coefficient, and the diffusion coefficient scales as the root mean square fluctuating velocity times the mean free path in gases. Same is true in the case of momentum diffusion and in the case of energy diffusion. Okay. In the case of momentum diffusion, it is the momentum that is being transported. In gases, that momentum is transported by the physical motion of molecules, as in the case of mass. Similarly, energy is transported by the physical transport of molecules, because there is a slight difference in the internal energy across a surface if there is a temperature variation, and that is what transports molecules across. And therefore, in gases, the mass, momentum and energy diffusion coefficients are all the same, of the same magnitude. They all scale as the mean free path times the fluctuating velocity, because the flux is equal to the fluctuating velocity times the difference in concentration. That difference is the mean free path times the gradient. Okay. So, the diffusion coefficients are all the root mean square fluctuating velocity times the mean free path. We had made some estimates of the mean free path in gases at room temperature. It varies from about half a micron to about 0.06 microns. The RMS fluctuating velocity is approximately the speed of sound. It is about 300 meters per second in air and oxygen, and about 1200 meters per second in hydrogen. On that basis, all diffusion coefficients are roughly about 10 power minus 5 meters square per second. In liquids, the mechanisms are different. Mass diffusion still requires the physical transport of molecules, because I had shown you in this case, okay, if one molecule is to move in one direction in a densely packed cluster of molecules, then the other molecules have to move out of the way. Therefore, a single molecule motion is not sufficient for diffusion. You require cooperative motion of many molecules, and due to that the diffusion coefficient is lower than what you would expect on the basis of the mean free path, the molecular scales and the root mean square fluctuating velocity. In liquids, momentum diffusion is relatively fast, okay, because you do not require molecules to move out of the way. Momentum can be transported by intermolecular interactions. So, momentum can be transported from one molecule to the next due to molecular contacts, and therefore, momentum diffusion is much faster in liquids. The momentum diffusivity is of the order of 10 power minus 6 meters square per second, whereas the mass diffusivity is of the order of 10 power minus 9 meters square per second in liquids for small molecules. The thermal diffusivity in liquids depends upon the mechanism. Okay. As I had tried to explain you in the last lecture, the thermal diffusion coefficient depends upon how energy is transported. If it is due to intermolecular forces, you get a relatively small thermal diffusion coefficient of the order of 10 power minus 7, whereas in special situations like liquid metals, for example, energy could be transported through the electron gas around the nuclei in a liquid metal, and that results in very fast transport. So, that in sum is in a summary is diffusion. Okay. And now, these two mechanisms, convection and diffusion, we will use in order to solve some problems. Okay. Simple problems of unidirectional transport first. Okay. So, let us start off with unidirectional transport. Where transport takes place in only one direction. Okay. So, the basic ingredients we have are the fluxes due to convection. So, what we will try to do is to write a balance equation for a differential volume, okay, where we write the rate of change of mass, momentum and energy within a volume is equal to, okay, mass, momentum, energy in minus mass, momentum, energy out plus accumulation. That is going to be the basic balance, and for these two terms, what comes in and what goes out can be either due to convection or due to diffusion. Okay. In the case of convection, the fluxes, okay, J is just equal to u dot n, the velocity dotted with the unit normal to the bounding surfaces, times concentration density, energy density or momentum density. Okay. And the flux due to diffusion is given by the diffusion coefficient, okay, okay, times the gradient, okay, okay, across the surface, the variation across the surface. This should be the variation in the direction perpendicular to the surface. Okay. So, those are the basic, okay, or rather minus alpha into the variation in the energy density. This is equal to, I had explained in the last lecture that when we consider momentum diffusion, we consider the viscosity, the positive sign for the viscosity, because the increase in momentum of a surface with outward unit normal is considered to be positive, and this is partial u x, partial u by partial x. Okay. where x is the direction of variation, okay, of the mass, momentum or energy. So, those are the basic ingredients that we will use. Consider a definite problem. We have a surface, okay. Let us consider the surface to be of infinite extent along the plane with a unit perpendicular to the surface is in the z direction, and along the plane we have the x and y coordinates. Okay. We will consider the surface to be of infinite extent, so that there is no variation in the x and y direction. Okay. And we will consider the fluid above the surface to also be of infinite extent. Okay. So, initially the fluid temperature, we will consider a heat transfer problem first. The fluid temperature everywhere is T infinity. Okay. Okay. So, initially the system is prepared in such a way that the fluid temperature everywhere is equal to T infinity, some temperature, okay, let us say room temperature. At the initial time, T is equal to 0, we instantaneously heat this bottom surface, okay, and apply a different temperature to this bottom surface. T is equal to T0 at z is equal to 0. Okay. So, if you look at the temperature profile, okay, as a function of position across, as I said, there is no variation in the x and y direction. If you look at the temperature profile, initially everything is at T infinity. Okay. So, if I take this as the temperature axis, everything is at the temperature T infinity. At time t equals 0, you are increasing this to T naught, okay. Okay, and therefore, everything is at T infinity, and as time progresses there will be a diffusion of heat from the surface, and the temperature will start to rise in some manner, okay, away from the surface. And what we would like to find out is how the temperature rises, what is the flux from the surface, how does the flux vary with time. Okay. This is of course an idealized situation. Okay. You could consider it, for example, an idealization of if you have a container which contains some fluid in it, okay, at some temperature, okay, and you instantaneously put it onto a burner, okay, which is at a higher temperature, okay, okay, at a higher temperature. Okay. So, initially the fluid was at room temperature, that is T infinity, and at time t is equal to 0, instantaneously you put this at temperature T0 here. Okay. So, there is an idealization of that problem. Instantaneously you place the container on this, and this fluid can be considered to be infinite, of infinite extent, so long as, okay, as time progresses the temperature profile will of course change. Okay. Initially it will be heated only here, as time progresses the temperature profile will change. Okay. The infinite fluid idealization is valid so long as the distance over which the temperature has increased is much smaller than the total height of the fluid. Okay. So long as the distance over which this temperature disturbance due to the base has penetrated, that distance is much smaller than the total height of the fluid. In that case you can consider it to be an infinite system. Okay. So, that is the problem. Okay. So, to be more precise, okay, for t less than 0 the temperature is equal to T infinity for all z. Okay. For t greater than 0, T is equal to T naught at z is equal to 0. Okay. So, that is the hot temperature. So, T is equal to 0 or T greater than 0, the temperature is maintained at T naught, okay, at z is equal to 0. However, if you go far from the surface, since this is an infinite fluid, if you go sufficiently far from the surface, the temperature is going to be equal to T infinity. So, okay, T is equal to T infinity as z goes to infinity. Okay. Okay. If you go sufficiently far from the surface, the temperature is equal to T infinity. Okay. So that is the problem that we have to solve, and that we have to do by doing a balance. Okay. Now, what do we do in a temperature balance? Okay. We take a small, okay, slice of the fluid of height delta z and cross sectional area A. Okay, we take a small slice of the fluid of height delta z and cross sectional area A, and we write a balance for this. Okay. The rate of change of thermal energy within this volume, okay, the rate of change of thermal energy within this volume is equal to what comes in minus what goes out plus any sources or sinks, okay, within this differential volume. Okay. Now, what is the rate of change of energy? Okay. Okay. So, okay, let us consider a time interval delta t. Okay, delta t, small t. Okay. Within this time interval, what is the change in energy? Okay. The energy is equal to, if we assume that it is a constant pressure process, that is, it is open to the atmosphere, then the energy per unit volume, okay, E is equal to rho Cp times T, okay, at the location, at the height z and the time t. Okay. This is the energy density times the volume is the total energy. Okay. Therefore, the total energy is equal to rho Cp T at z and t times the volume. Okay. The volume is equal to delta z into the cross sectional area A. Okay. So, that is the total energy within this differential volume. Okay. Now, the change in energy within a time delta t, okay, is going to be equal to, okay, E at z t plus delta t minus E at z t. Okay. If we consider the density and the specific heat to be constants, okay, then this will just be equal to rho Cp t at z t plus delta t minus t at z t, okay, into the volume, which is delta z times A. Okay. So, that is the change in energy, okay, within a time delta t. Okay. So, change in energy in time delta t, okay, is equal to energy in minus energy out, okay, plus any accumulation. Okay. That is a basic balance. The change in energy in a time delta t, I had said, was equal to rho Cp into t at z t plus delta t minus t at z t into the volume, that is the area, into the height. Okay. Now, what is the energy coming in at the location z? Okay. Energy coming in at the location z. Okay. The energy in at the location z is going to be equal to the thermal diffusion coefficient times the temperature gradient at that location. Okay. So, therefore, I will get, okay, this will be equal to, okay, the flux at the location z, okay, at the location z. Okay. Energy in is the flux is energy per unit area per unit time. Okay. Therefore, the flux at the location z times the area times the time interval is going to be equal to the energy that is coming in, okay, at the location z. Okay. So, it is going to be equal to the flux times the time interval times the area. Okay. That is the energy that is coming in at the location z. Okay. The energy leaving at the location z plus delta z is once again equal to the flux at that location z plus delta z times the area times the time interval, because the flux is equal to energy transported per unit area per unit time. Okay. So, this is going to be the energy out, the flux in the z direction at the location z plus delta z times delta t times the area. Okay. And this accumulation term, if there is any source of energy within that element, okay, let us say because there is a reaction within that element, or there is some either phase change within that element, okay, the source of energy within that element, okay, so I should write this as source rather than accumulation. Okay. This will in general be a source density, a source per unit volume, okay, a source density times the volume itself, delta z into A. So, this S, okay, is energy accumulated. So, this energy source S is an energy generated per unit volume per unit time due to a reaction. Okay. So, for example, if you have a certain reaction taking place, there is a certain amount of energy that is generated per unit volume of the fluid depending upon the concentration of the reactants per unit time. So, that has to be multiplied by the volume and by the time delta t. Okay. So, that is a fundamental balance equation. Okay. And once we have this, we can divide throughout by the volume A times delta z, divide throughout by the time delta t, okay, to get an equation. So, you write down for each differential volume for each interval of time, divide by the total volume and divide by the time interval. Okay. So, if you divide by the volume and the time interval, you will get rho Cp into t at z t plus delta t minus t at z t. Okay. When I divide by A delta z times delta t, I will get a delta t here. Okay. I will get qz at z minus qz at z plus delta z, okay, divided by delta z, okay, plus the source of energy. Okay. Now, we go from to a differential volume and a differential time interval. Okay. Take the limit delta t going to 0 and delta z going to 0. Okay. When you take that limit, you get a derivative with respect to temperature with respect to time on the left, and the derivative of the flux with respect to z on the right. Okay. So, you will get rho Cp partial t by partial t, okay, when you take the limit of time interval going to 0. This on the right side, okay, is q at z minus q at z plus delta z divided by delta z. Okay. Normally, we write the derivative as q at z plus delta z minus q at z divided by delta z. So, this is basically the negative of the derivative with respect to z. Okay. So, this is equal to minus, okay, q at z plus delta z minus q at z by delta z. Okay. I just written it with a negative sign outside. Okay. And now, this term here you can recognize as the derivative dq by dz. Okay. In this case, it is a partial derivative because we have variations both in z as well as in time. So, this is now a partial derivative minus partial qz by partial z, where qz is the flux in the z direction, plus any source of energy, okay, plus any source of energy. I should write that as S. We know that the flux was equal to minus k times partial T by partial Z. That was Fourier's law for heat conduction. Okay, flux was equal to minus k times partial T by partial Z. Okay. So, if I substitute that in this equation, I will get rho Cp partial T by partial T is equal to minus K d by dz of partial T by partial z plus the energy source, okay, per unit volume per unit time. Okay. This is of course assuming that the thermal conductivity K is independent of temperature. Okay. That is the assumption that we are making here. Okay. So, if you use that assumption, then I will get an equation for the temperature field as rho Cp dt by dt is equal to, I am sorry, this should be a plus sign here. Kindly note this mistake. So, there is a minus sign over here. There is a minus sign over here in dq by dz, and qz itself has a negative sign. So, in the end you will get a positive sign in the equation for the temperature field. Okay. So, you will get k d square t by dz square plus Se. Okay. Alternatively, if I divide throughout by rho Cp, okay, I will get partial T by partial T is equal to K by rho Cp partial square T by partial Z square plus Se by rho Cp. This of course is the thermal diffusion coefficient. Okay, this K by rho Cp is the thermal diffusion coefficient. Okay. So, the final equation that I am getting is of the form dt by dt is equal to alpha d square t by dz square plus S by rho Cp, okay, where alpha is the thermal diffusion coefficient, and you can see that when the thermal diffusion coefficient has dimensions of length square per unit time, then you get correct dimensional consistency in this equation between the time derivative and the spatial derivatives. Okay. So, this is the thermal diffusion coefficient for unsteady diffusion in one dimension. Okay. We will see a little bit more about the analogy between this and mass and heat diffusion in the next lecture, and then we will look at how to solve these problems. Okay. So, we will continue this in the next class. Okay. I will see you then.